Okay, so here we are again in the morning looking at my cool platinum crystals. This one is something I'm working on and kind of taking the time to polish it up a little bit at a time. And I'm using hand tools like no, no, I can't find it at the moment. There it is. This is a piece of marble, dolomite marble, and so it's metamorphosed from calcium carbonate, basically, and it has become a fairly solid and substantial chunk of stuff. And it's actually white. it's it's just kind of grayish because I've been um, polishing this guy on here. So, and it gets pretty shiny because this is probably the whitest metal in the entire world. Now it's really shiny. It's getting better. I mean, it doesn't look really great right this second, but it is actually getting better. And you can see planes of cleavage on here more than actual scratches. Planes of cleavage are part of the close packed cubic hexagonal arrangement of the atoms. So this is a crystal structure that's called a dendrite, and that means that they make leaf-shaped metallic crystals. And that's what that is. It's a leaf-shaped metallic crystal of platinum. Very, very, very cool. It makes hoppers, cubes with hoppers. And hoppers are dished in places where it kind of spirals down the staircase into the hopper. And it does so all over the entire surface of the metal. That's why platinum is used in literally hundreds of chemical reactions in the laboratory as a catalyst because of these hoppers on its surface. And it's very, 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 very non-reactive. And the thing about a catalyst is that it does not participate in the reaction that it facilitates. So there can be all kinds of cool chemistry going on inside those little hoppers. But all the platinum is doing is just providing a place for it to happen. It's not actually making it happen. to a certain extent, anyway. In this case, it was very high temperature, plasma passing through dust, volcanic ash. The volcanic ash that was laid down during the KT extinction event, which was had at least two planet-wide periods of volcanism, widespread volcanic activity across the entire planet's surface. You know, when I first started out, the books tell you that it's like a few centimeters of volcanic ash that you might find out there somewhere. I've been out there looking, man. You're walking around on top of it for the most part, okay? So, which is what makes it kind of funny. Because I'm just walking around on top of it looking for it, man. And so is everybody else, except they didn't know they were looking for it. But we have them because this came from the dust my wife picked up out of the middle of the road. Okay. Dust from the middle of the dirt road. My wife and I brought it home, and it's in a little bucket over there in my bathroom laboratory. I've got a tiled bathroom where I can do chemistry without worrying about burning the house down. We are going to melt some of this with an induction furnace today. So, maybe it'll be a little less dramatic and we'll have a little more actual metal to work with. Because I believe I know how to do this all the time, pretty much all the time. It was not luck. This was a prediction from available information. I started finding little crystals, silver crystals, with hoppers. And the hoppers light my fuse, man. Hoppers light my fuse because I know what platinum is. I haven't ever been able to afford any. I actually bought some that were about the size of, see this little piece here by my thumbnail? About that big. And maybe a little smaller, maybe a lot smaller. And I bought a gram of these little cubes that had hoppers, just like that, on one side, and cube bingani on the other. And I was pleased as punch to pay $30 for that, I don't know, 10 years ago, 10, 12 years ago, something like that. because this madness that there might be more platinum in the environment than anybody ever even dreamed of came about as the result of trying to make precious opal in a jar with my friend P. Michael Hutchins from MIT. And I ended up with some jelly type stuff, kind of clearish jelly type stuff that looked like opal to me, but it did not, in fact, have a play of color. P. Michael says to me, Rick, it could be any fucking thing, man. I got mad. I said, well, the book says that it's feldspar and it does this, that, and the other. And I traced a chemical reaction that I had come up with to explain what I had done. I had done it some years before, and actually ended up with precious opal, with an opal that had a play of color. But I used clay from Lightning Ridge. Okay? And what I was doing with Pete Michael was using commercial clay because I couldn't get anybody in Lightning Ridge to send me some in the kind of quantities that I want to work with. And so I got a bucket full of clay from Georgia, right? Kaolinite clay. And and it didn't work, right? It didn't work. Did not make opal at all. In fact, it was relatively inert. Um, I mean, it appeared to be inert to me at the time because I was looking for a vigorous exothermic reaction. Um, and you actually do get it when you start making opal in a jar. Um, and that's the surefire indicator that you're on the right track. And so apparently not all kaolinite clay is the same, right? Is what I'm thinking. And it turns out that I just didn't have the right information. Because there is no feldspar. There's no feldspar. No silica. Silica is not silicon. Silica is silicon dioxide. Presumably the most common thing on the planet, but it's not. This is. This stuff is AUPT. And there is no, I've been looking, and there's feldspars in volcanic ash when it first gets laid down. And so if you go out and you get fresh volcanic ash, and you like put some vinegar on it, okay? Vinegar is a nice, very light acid, and it foams up, man, like crazy, because the calcium and the sodium in the volcanic ash react with the acid. So, I know that there's feldspars in there, but when you get the weathered volcanic ash of Lightning Ridge, there's apparently something that goes on that creates a precious opal that is 5.5 on the Mohs scale of hardness. Um, Now, that's not the only thing that does that. And nobody knew that before. And so, but diamonds do it. Diamonds do it very nicely. Probably better, actually. Better. And silicon carbide. Silicon carbide mixes with carbon from diamonds at great depth. And so if that depth happens to be the right size, it can create planes of cleavage that are the right size to break light into its component colors. And I happen to know of several lakes full of what I believe are silicon carbide that has been called iris agate because it creates rainbows in kind of stripes that look like the iris of an eye. So, and I know where there's several lakes full of these things in a whole river valley. And I'm going to move up there pretty quick here, I think. So, and then I'll show you because there's lots of it. It's not scarce or rare.